Alright, so next part is the discrete Fourier transform of periodic signal and the discrete Fourier series. Alright. So in this part, the important equation is T equals to NTS. This equation has used during the sampling chapter. And next is the specific frequency is equal to 1 over NTS. N is the number of sample. So this is how we can change the discrete signal to the continuous times. Okay, this is the example 4.3. So for example, in the question, it give you the discrete signal xn. So we can see the signal in this graph. 0 at n equals to 0, the value is 0, and n equals to 1, we have 0.9511, and next is 0.5878 and negative 0.5878. So we need to find the discrete Fourier transform. So the DFT we can calculate by using the definition. Okay, so this is the discrete signal. So we can use the definition to calculate the DFT and use the button option in the calculator to find the value of k equals to 0 until k equals to 4. So actually in this question, the answer will be only until this part. Actually, we want to show from the DFT how we can find the value of continuous time or the original signal equation in time domain. We can use the DFT signal to calculate the magnitude and phase, and then we can find the equation of the signal in time domain. So this is the equation to find the magnitude. In this case, we will use the single spectrum. So the equation is 2 times the real value to the power of 2 plus imaginary value to the power of 2 divided by the number of sample. So for k equals to 0, the magnitude will be 2 times 0 to the power of 2 divided by 5, and we will get 0. At k equals to 1, we can find the magnitude of xdft1 by multiplying 2 times the square root of real value 0 to the power of 2 plus the imaginary negative 2.5 to the power of 2 divided by 5, and the answer will be 1. And lastly, for k equals to 2, we can find the xdft2 2 times square root of real value 0 and imaginary value of 0 divided by 5, and the answer will be 0. So this is the magnitude, and then we need to find the phase of the signal. To find the phase at tangent of imaginary divided by real, and we just use the for k equals to 0, the imaginary is 0 and the real is 0. We have 0 at tangent 0 is 0. And then for k equals to 1, we have imaginary negative 2.5j and the real is 0. So negative 2.5 divided by 0, we will get a negative infinite. At tangent negative infinite is negative pi over 2. And the same for k equals to 2, we will have the imaginary value of 0 and real value of 0. At tangent 0 will be 0. And you can calculate the k equals to 3 and k equals to 4 and check your answer with the one that I have shown here. So previously we have calculated the value of magnitude and phase. So this is the magnitude value, and also this is the phase value. So from the magnitude and phase, we can calculate the signal, or we can find the equation of the signal in time domain. So this is the equation, the summation from k equals to 0 until n minus 1, magnitude times cos 2 pi f k t plus psi. So this is the phase, and this is the frequency, where the k is the frequency at the specific harmonics. So for example, k equals to 0, which is f naught equals to 0 Hz, k equals to 1, f1 equals to 1 Hz. So the value of magnitude we will multiply with the trigonometric here. So the first k equals to 0, the value is 0, so 0 plus, at k equals to 1, we have magnitude 1 cos 2 pi, f1 is equal to 1 Hz, t plus psi, our psi at k equals to 1 is negative pi over 2, and at k equals to 2, we have magnitude of 0, and the f2 is equal to 2 Hz plus psi, our psi is equal to 0. So this equation can be used for the single sideband. For the spectrum, actually the value will be the same like this one. At the folding index, the value of 2 will have the conjugate at k equals to 3, and the value at k equals to 1 will have the conjugate value at k equals to 4. But we just use the first part here, 0, 1, 2, to calculate the signal in time domain by using this equation. So at the end you will get the answer cos 2 pi t minus pi over 2. So for the cos 2 pi over t with delay pi over 2, we will have the same signal as sine 2 pi t. Alright, so that's all. Alright, all the best.